friends, my name is Biswas and welcome back to my YouTube channel. In this channel, we do some activities, some experiments and discuss about some useful concepts in science and mathematics. My today's topic is simple harmonic motion. Since I am going to cover up many aspects of this kind of motion, so I have taken it into few parts. So today I am taking up the first part. In this part I will be discussing about what is simple harmonic motion, and then we will be discussing about a simple pendulum because it exhibits simple harmonic motion, and then we will discuss about its time period, how much time it takes for one oscillation, and then we will also see the factors that affect the time period. So let us start with simple harmonic motion. It's a type of motion in which simple harmonic motion, which is also known as SHM, is a type of motion in which the acceleration is directly proportional to the displacement. That is, acceleration is directly proportional to displacement. Directly proportional to displacement. What does it mean? It means if you take a simple pendulum and then displace it by a small amount, then it will have a small acceleration towards the mean position. On the other hand, if you make a larger displacement, then it will have more acceleration towards the mean position. That is what we call as the simple harmonic motion. Acceleration is directly proportional to the displacement. Now, simple harmonic motion is exhibited by many objects such as a simple pendulum, maybe a swing, maybe a loaded spring, and all those things. So today we are going to discuss about the simple pendulum. So it is a metallic bob. It's a metallic bob which is suspended from a support with the help of a massless string. So here we have tried to make a simple pendulum by taking a bob and we have suspended it from a support with the help of a massless string. The length of the string is taken as capital letter L. The radius of the metallic bob, the radius of this bob is taken as small r. We can find the radius of the bob by taking the help of a vernier caliper. So this is a device called vernier calipers, and by using this vernier calipers we can find out the diameter of the bob, and then we'll divide the diameter by 2. That will give us the radius of the bob. And when you add the radius of the bob to the length of the string, that gives you the effective length of the simple pendulum. So effective length is equal to length of the string plus radius of the bob. And the meaning of time period, it is the time taken by the simple pendulum for one complete oscillation. That means starting from one extreme position, going to the other extreme position, and then coming back. Starting from one extreme position, going to the other extreme position, and then coming back. This is called one oscillation. And the time taken for one oscillation is given by the formula T is equal to 2 pi square root of L upon G. This L is called effective length of the pendulum, and this G is called the acceleration due to gravity. So let me write it here. L is the effective length and G is the acceleration due to gravity. So on what factor the time period of the simple pendulum depends? Does it depend on the length of the pendulum? Yes, of course. Does it depend on the acceleration due to gravity? Yes, of course. Okay, so now the factors on which time period of a pendulum does not depend. First factor is mass of the pendulum. Second factor is displacement from mean position. So let us check the first factor on which the time period does not depend. It is the mass of the pendulum. So this is my pendulum and I will take it to the extreme position and I will let it oscillate for say 10 oscillations, and then we will find out the total time taken for 10 oscillations and we will divide it by 10, and that will give us the time taken for one oscillation. And after that we will increase the mass by adding one more bob to it, and we will check the time period again and we will see that the time period does not change at all. So let's start. So I take this pendulum to the extreme position A, and from here I will let it oscillate for 10 times. So 1, 2, 3, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Now I have got another bob in my hand, so I will add this bob to the previous one. That means now the mass of the pendulum is increased by 2 times. So if the mass of the bob earlier was m, now it is 2m. Let us check whether there is any change in the time period. So we'll perform the same. We'll take the bob to the extreme position and we'll let it go for 10 oscillations, and we'll check what is the time period this time. So 1, 2, 3, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Now let us find out the time period in both the cases, and you can see that the time period remains the same with some errors that will always be there. Okay, so now the second factor is displacement from mean position. Displacement from mean position means now the pendulum is resting at its mean position. So if I displace it by some amount, maybe small, maybe large, is it going to affect the time period? So actually what happened, this was first time observed by Galileo. So that time there was no clock, no watch. So he had to use his pulse rate to check the time period of pendulum, and he found that within a small angular displacement, the time period is independent of the displacement. That means if these angles are small, then no matter how small is the displacement or how large is the displacement, time period remains the same. Why? Because if the displacement is small, then the acceleration will also be small, because it is a simple harmonic motion. And as the acceleration is small, that means it will take more time for one oscillation. On the other hand, if the displacement is large, then there will be more acceleration towards the mean position, and that makes the time period small. So in a way they nullify each other. So no matter how much is the displacement within a small angle, the time period is independent of the displacement. So when I make a small displacement, it is moving slowly. And when I make a large displacement, it is moving fast. So overall effect is there is no change in the time period which was observed by Galileo by using his pulse rate. So what I will do, I will take one more pendulum here, and these two pendulums are having the same bob mass. So the mass of the bob are same effective length. So I have maintained the same length. So this one I will displace by more amount, and this one I will displace by small amount, and you will observe that the time period of the the oscillation remains the same. So let us start. This one is more displacement, this one has a less displacement. So let's observe what happens to the time period to both of them. So if you calculate 10 oscillations of both of them, then you will come to know that there is no change in the time period due to change in the displacement of the bob from the mean position. It means displacement from the mean position does not affect the time period within a small angle of displacement. Now, the factors on which the time period of a pendulum depends. First factor is effective length of the pendulum, and second factor is the acceleration due to gravity. So to check the effective length of the pendulum, how does it affect the time period of a pendulum? Let us make the length of this pendulum small. So I can make it a small length by tying it from the top. So that makes the effective length small, and other one I maintain the same length. Now we'll oscillate both of them. Now what is the same in them? The bob mass is same in them, and we will go for the same displacement also. We'll not make them different displacement, and then we'll check what happens to the time period of them due to the difference in the effective length. As you know, the time period is directly proportional to square root of the effective length. Time period is directly proportional to square root of effective length. That means as the length of the pendulum will increase, the time period will also increase. So let us displace them by the same amount, and let us find out which one is moving faster and which one is moving slower. Which one takes more time for one oscillation, which one takes less time for one oscillation. You check. The smaller one is moving faster, so that means it is taking less time for one oscillation, and this one is moving slower. That means it is taking more time for one oscillation, and that tells you that the time period is directly proportional to length of the pendulum. If I increase the length of the pendulum by 4 times, then the time period will be increased by square root of 4, that is 2 times. If I increase the length of the pendulum 9 times, then the time period will be increased by square root of 9, that means 3 times. So this is the effect of the effective length of a pendulum on its time period. And the next one is acceleration due to gravity. Acceleration due to gravity, the time period is inversely proportional to the acceleration due to gravity. So the value of g on earth, that is GE, is equal to 9.8 meter per second square, and the value of g on moon is 1.63 meter per second square. So it tells you that if a pendulum is taken to the surface of the moon, since the value of g on the moon is less, so the time period is going to be more. That means the pendulum will oscillate slowly. On the other hand, if the pendulum is taken back to the earth's surface, the value of g is 9.8, which is large, and therefore the time period is going to be less, and that means the pendulum will start to move fast. So that's it about the factors of time period. So we come to the end of part 1. Part 2 will take up in our next video. Until then, goodbye.